Hi everyone, I'm Dr. Challa, Krishnaveer, Abhishek. I've completed my PhD in linguistics. I've authored a few books on topics pertaining to applied linguistics, psychology, and mass communication. So basically, I recently started my journey into spirituality, and I'm currently working on soft skills through Bhagavad Gita, being a soft skills trainer. So attending SohamVidya's 10-day program in both in Telugu. I've attended in Telugu and English, and I've learned a lot. I've actually tried to understand the tenets of Sanatana Dharma. And slowly, as a Sanatana Mitra or a Hindu Mitra, I would want to contribute back to the society. Thank you.
The first scenario will be to Abhishek, Krishnaveer Abhishek. Are you ready for that?
Yes, sir.
Okay, perfect. All right. Okay, so Abhishek, you are Naveen for now. Okay, you're not Abhishek, so I'll call you Naveen. So Naveen, it's your golden chance. I don't know how you're going to use this golden chance. So you're employed in a shop, and the shopkeeper is a kind employer. He always ensured the welfare of his staff just as much as he cared to allow his business to grow. Okay. Over the years, you have gathered wealth of experience and enough savings to start your own shop. Now you're all really set. You're all set to start your own, shop and be your own boss. In fact, you're planning to inform your boss about the same. However, before you could do that, the shopkeeper made an unexpected financial loss to the extent that he will have to sell his shop. You started thinking a lot about what to do, and what will you do, Naveen?
Hi guys, I'm Naveen. So I was recently employed in a shop. 2 years ago, I got an employment in a shop, which is owned by Chaitanya Garu. He paid rupees 10,000 per month. He was a very kind employer, and he always took care of welfare of his staff like his own children. Over the years, what I've done is, apart from working in the shop, I've also done some part-time jobs and I've gained some wealth. And now I want to start my own shop. So I'm planning to inform Chaitanya Garu. But I understood that he's in financial distress, and at this time he needs my help. But at the same time, I have a lot of obligations. I have to perform my sister's marriage, and with 10,000, I don't think it's possible. And I have to take care of my ailing parents. I have to take care of their health also. And there's a lot of medical bills, so I have to take care of them also. So there's lakhs of money that I have to earn and pay. So with 10,000, I don't think it will work out. And for me, my parents and my sister, they are the priority. But at the same time, Chaitanya Garu, he took care of me like a father. So he paid 10,000, though the salary was less. He was very kind to me. I learned a lot from the shop. So as the shopkeeper as Mr. Chaitanya Garu was very good to me, I'll put forth two options before him, two feasible options. Actually, as Sir said, gain predominant, that is individual benefit, and at the same time holistic benefit. So these two options are based on the holistic benefit that both of us might get, not just Chaitanya Garu or not just me. So the first option I would put before him is, so I'll ask him, because anyways he's contemplating to sell his shop and he's in a lot of financial distress. I'll ask him to sell his shop, and I'll give him a proposal where he can be my partner in the new shop that I'm planning to start. So because his expertise, he's been in this business for more than 10 years. So his expertise would help me a lot, and having a genuine partner like him would be of help to me. So, and also I would give him a second option if he says that, he's not interested to start a new shop, or he wants to continue with his old one. So I'll suggest him an equally competent individual who would assist him in my place instead of me. So
Right,
I think both these options would be good for Chaitanya Garu.
Well, you made it extremely interesting. You actually turned it turned it around to kind of make it a lot more realistic, I would say, because you actually brought in certain of your own problems in your own personal life, and you're just trying to look at How do I justify my own expectations of my own life? How do I meet my own challenges? At the end of the day, there is life beyond the shop as well. So you nicely kind of brought in a very good 360 degrees scenario of your life. Of course, it was beyond the script. That's good. That's good. I enjoyed it. I enjoyed the way you've narrated it. So
Thank
let's
you, sir.
look at it this way. Um, if you've done a fantastic job in thinking about the shopkeeper, your own boss, who has been kind to you, and you want to be kind to him as well. I mean, you can actually easily walk out of the situation saying, okay, I have nothing to do with him. I made up my mind. I'm going to invest in my shop. I don't want anything to do with his problems, right? So that would have been typically gain predominant solution, isn't it?
Yes, sir.
Personal gain predominant solution. So instead, you actually are looking at the holistic benefit predominant solution, which is good. Now, when you propose to the boss, become my partner, I will buy the shop, what do you think would be his reaction?
First thing is, because as far as it's concerned to me, I've actually prepared Chaitanya Garu that, in the near future, maybe I would start my own business, but not now. But this will be a slight shock to him. But definitely, I think he would contemplate on my proposal
Sure.
instead of
Yeah.
getting.
So certain things we may actually notice is people may start becoming a little jealous or insecure.
Yes.
I mean, until now, I was the one who provided business jobs to Naveen, and Naveen is now in a position where he's actually trying to dictate terms as well. So, what kind of equation does it do you really need in this scenario for both of you to be effective partners? What equation do you expect between both of you?
The first thing is, it's very important for me to build a trust before directly giving out the proposal. So I have to start narrating my own problems, because everybody has their own problems.
Very nice. Yes.
Everybody is in financial distress. So I'll start narrating my own problems. And, when we start sympathizing or empathizing with each other, then I'll put forth a proposal that, this might also be good. Just I got an idea that this might be a good thing if both of us can work it out together. So I'll start as a victim, and then I'll put forth the proposal instead of putting the upper hand.
Right, right. I mean, I don't think even you need to do that victimhood role. In fact, I call this honest communication.
Yes.
Honest communication actually resolves a lot of issues. So when you honestly put forward your position, because I'm sure there is an expectation that I have looked after my staff well, so it's their turn to look after me now. But actually, he's a kind employer, and I'm assuming that he is also very grounded as well. But forget
Yes.
all that. An honest communication whereby you are putting forward not only your proposals for the shop and the future of it, but you're also putting across what are your concerns, what are your expectations and aspirations as well. So
Yes. Yes.
we called it the churning, just as we are
Yes.
doing this churning here, where I'm asking you questions, you are providing answers. The same
Yes.
churning happens between you and Chaitanya Garu, to bring out the best solutions out there. So the churning is only possible when both parties can honestly engage in that discussion.
Yes, sir.
It's beautiful. All right. Okay. I think given the time, wonderful. I've enjoyed the way it went. I
Thank you,
hope others have also enjoyed it. I would ask Amulya, Sampada, or Akhil to make any quick comments if you have. Amulya, you want to say something?
Yeah, it was a great story, and I really like the perspective. Like, I was thinking more like maybe share. You have the money, so you could put some into the family and all, and you could give some. But yeah, the solution was really good. I mean, this is a
Yeah.
fresh perspective. I like
See,
this.
yes, I think at the end of the day, what Dharma teaches us is whatever may be the proposals you have, I'm nobody to judge you whether you are right or wrong. So Naveen may go to Chaitanya to say, I'm outrightly buying your place. But does he have the right justification? And again, I come back to the honest communication part. What are the intentions behind it? And partnership, it could be, or anything else. So we are no one. Dharma actually teaches us not to judge others, because unless we are in that position, we won't really know. So definitely truth here, truth, honesty, and having that right kind of self-respect, as we call the Atma Gauravam, and compassion towards the shopkeeper, putting everybody into perspective. Nice.
Sir, I believe that as Hindus or as followers of Sanatana Dharma, so we are sticking ourselves to a brand, and we feel that we have to protect the brand when the brand is affected, or whenever someone questions our dharma. So we feel that we have to answer them, or we have to protect our dharma. But I believe that by just following our dharma, because I believe that most of the Hindus, we are actually not following the dharma as it should be done. So if we just follow the dharma instead of answering them back verbally, if we just answer them back through our actions, then I think most people will be motivated to understand, or to come back to the dharma. The main problem is we generally talk about defending our dharma, but most of us, we are not putting it into action what we are preaching actually. So that is a main problem, and I believe that we need not protect our brand. The brand, the Sanatan Dharma will take care of itself
There's a
if we
nice,
follow it
yes, very
correctly.
true, very true. In fact, there are two things come out of this. There's a nice video by String videos on YouTube, and he talks
Yes,
about
sir.
it. He talks about this beautifully. He says it is about practicing dharma, not talking about dharma. Similarly, if you realize the realized dharma strategy that I mentioned in the video, this is all about practically applying it, looking at the relevance of past wisdom or ancient wisdom to the current times and applying it. So we can be scientific about it. We don't need to be dogmatic about it. So we have to look at the application, and how do we do that? We need to practice it in our life, and if it works for us, we should endorse it. And when we endorse it, we should automatically learn to practice it lifelong. And as we practice it lifelong, it's a time-tested skill. Then you can definitely teach others as well. And you're very right in saying that that's the way we need to go.
So basically now we're in the era of digital humanities, wherein students of humanities or researchers from humanities and students of technology and researchers of technology have to collaborate. So for example, I'm from linguistics. So when I try to collaborate with electronics, students of electronics and communication, then the amalgamation gives speech recognition. And for example, I'm a linguist. If I want to collaborate with computer science, it, the amalgamation gives computational linguistics or natural language processing that we do with Python. So machine learning, artificial intelligence, all these are aspects of interdisciplinary or multidisciplinary works. So I'm an advocate of multidisciplinary research, and most of my research outputs actually focus on this. So I'm talking about microelectronics because I'm currently doing a project along with my co-researcher, who is also my sister. She's Ms. Challa Shushmita. She's a research assistant in University of Louisville, US. So we are together. We're working on a paper, a research paper. So before that, actually, when I because my journey began as a student of engineering, and I've completed various courses on mobile communications, sustainable engineering, etc. So I understood that when you add social sciences to engineering, then it is complete. So that is the reason why I call myself as digital humanist. So I believe that so all social scientists they have to learn technology, and all technocrats should also learn social sciences like mass communication, political science, sociology, linguistics, law, management, all these aspects. So that's why, in your finally you have the subjects. So coming to microelectronics, this is our research area currently. Me and my sister are working together on microelectronic fabrication. So that's the reason why I've chosen microelectronics as my topic, because I would like to explain microelectronics in a way that a humanities person understands it, or maybe a school student understands it. I believe that, when you start with the basics, it will be easy for the receivers or the listeners to understand and comprehend what we're trying to say, because I'm a soft skills trainer. I talk about the process of communication. I understand the nuances of listening and understanding. So my talk is based on this. So we talk about microelectronics. So we have arithmetic operations, right? We have arithmetic operations like addition and subtraction. So similarly, we have real-time avionic operations like flight operations. So simple arithmetic operation and complex avionic operation. So from simple to complex systems, they comprise of switching devices. So from a simple system to a complex system, both of them comprise of switching devices. So switching devices play a major role from a simple to a complex system. Every system has the switching device. So when we talk about switching devices, we have to come to the basics of understanding how the switching devices are produced. So this is the base of microelectronics or electronics as such. So when you talk about conductors, conductors allow free flow of current. You know that. Insulators, they don't allow free flow of current. So conductors allow free flow of current, insulators don't allow free flow of current. So when you talk about microelectronics, we are actually talking about switching devices which are made using semiconductors. So semiconductors are between conductors and insulators. So when it is on, they allow the free flow of current. When it is off, they don't allow the free flow of current, the free flow of electrons. So semiconductor device is the basic device, is a basic microelectronic device. So we know about conductors, we know about insulators, and between we have semiconductors. So semiconductors are nothing but switching devices that are placed between a conductor and an insulator. So when they're in on state, they act like a conductor. When they're in off state, they act like an insulator. So examples of switching devices are, you have diodes, you have transistors, you have op amps, etc. So these are a few examples of switching devices. So you have electronics. So why microelectronics? Why is it micro? Why is it not macro? So we have to understand that. So my lecture will be based on why micro and why not macroelectronics, and why miniaturization or microing of electronic devices is important is also my topic of interest. So conductor is basically for examples of conductors are metals like copper and gold. The examples of insulators are glass and wood, etc. And the examples of semiconducting devices are silicon, germanium, etc. So this is the basic introduction that I wanted to give you. So you can see nanotechnology fact or fiction. So during 1950s and 60s, there were many different novels and miniature mans, miniature creatures that can enter our body, that can enter our bloodstream. But now, because of microelectronic technology, this is possible. So there are man-made devices which are of the size of red blood cells, that is 10 microns approximately, or 1/10 of your hair strand. Okay, so these are built now. So from fiction, this has become a fact, right? So during 1950s, 1950s and 1960s, there were fictions about traveling within a human body. And now that fiction is a reality. Through microelectronic technology, it is possible, right? So, but now it's a fact. So example, you can see, you have a famous fiction for explaining microelectronics, that is Ant-Man. It's a Marvel series movie. You can see that, you can enter the body, you can enter the bloodstream. Similarly, the microelectronic devices that we are building are able to enter our body and perform complex operations. So why we need small systems? So we need small systems in assisting, especially when it comes to health point of view. It assists in drug delivery, and it helps in conducting minute operations like brain surgeries and heart surgeries. So it actually makes surgeries risk-free, and because sometimes, for surgeries you can't use manual hands. So microelectronic devices are of great help in healthcare. So similarly, physiological testing of the functioning of human body can also done with the help of microelectronic devices. So microelectronics, has a lot of applications, and now we need to understand that it is no more a fiction, and it is a fact. So how small is a microelectronic device, or a microelectronic things of microelectronic amplitude? So when we talk about nanotechnology is something which is below 1 micron. 1 micron is nothing but 10 power minus 6 meters. So when an object, when a thing is less than 10 power minus 6 meters or less than 1 micron, then it is considered as nanoparticle. So a technology, electronic device that is less than 10 power minus 6 meters is considered into nanotechnology. If it is 10 power minus 6 or more than that, then if the measurement is more than 10 power minus 6 or 10 power minus 6, then it is considered microtechnology. So we know that 1 kilometer is 10 power 3 meters, right? And that is 1000 meters. 1 millimeter is 10 power minus 3 meters. Similarly, 1 micron, that is when we talk about microtechnology, we measure it in terms of microns. So 1 micron is up to 10 power minus 6 meters. Okay. Similarly, nanotechnology is between 10 power minus 6 to 10 power minus 9 meters. So for example, if you take your height strand, it can be up to 100 microns. Similarly, dust particles can be from 1 to 5 microns in size. So that's why you can't see them with your naked eye. So similarly, your blood cells, your red blood cells and all, they're up to 10 micron size. Your bacteria is 0.5 micron or 500 nanometers. Okay, your virus is 50 nanometers, your DNA is 20 nanometers, your protein is 10 nanometers, and an atom, the most indivisible object, that is an atom, most indivisible particle, the atom, is 0.5 nanometer. So when we talk about electronic devices, so these electronic devices, because we talk about microelectronics, they are in these ranges, in the ranges of microns. So, for example, the general size of a silicon wafer. So, a silicon wafer is basically an unprocessed device. It's like a circuit, where semiconductor devices are stuck on. So, that is up to 10 centimeters. So, similarly, a microchip, a processed semiconductor device, a microchip, which contains all these processed semiconductor devices, that microchip is actually, its measurement is 1 centimeter. So in 1 centimeter, there are multitudes of transistors, multitudes of diodes, the multiple different triodes. You have different devices, you have resistors, you have capacitors, you have inductors, you have a lot of things in 1 centimeter chip. So within small size, the electronic functionality is carried out. So these small devices even have, when the device itself is so small, when they're in microns and in nanometers and in centimeters. For example, the integrated circuit itself is in centimeters. You can imagine the small microelectronic devices. They might be in, micrometers, macrons, or nanometers. So they'll be very small. So if the device itself is very small, then the values of measurement, you can imagine the values of measurement, they will be very, very minute. So that's why you have pico, femto, and atto. 10 power minus 12 meters is pico, 10 power minus 15 is femto, 10 power minus 18 is atto. So the values of measurement of capacitance and inductance of these small microelectronic devices will be in pico, femto, and atto. That's the reason why we have these values of measurement too. So this is a so there were no semiconductor devices. So, but there were switching devices. There were switching devices, but there were no semiconductor. Semiconductors were not discovered actually. The usage of semiconductors was not understood during this time. So in 1904, so before there were no semiconductor devices. So in 1904, the first diode was built by John Fleming. And similarly, the first triode was built by Lee De Forest in 1906. So then also there were switching devices during these times also there were switching devices like diodes, triodes, and transistors. So this how can this be achieved without having a semiconductor device? Yes, this can definitely be achieved. For example, you can take the case of a bulb. So this was achieved actually through vacuum tubes. So the best example is bulb. But the main problem with the bulb is basically it is very big and it consumes a lot of space. So it is up to 2 to 4 inches. So it is very difficult. So what happens is in a vacuum tube, during those days when semiconductors were not known, in a vacuum tube, a cathode and an anode were placed. So the cathode is basically high concentration of electrons. And an anode is basically low concentration of electrons and high concentration of holes or positive charge. So because cathode has high concentration of electrons or high density of electrons, it has negative charge. Because anode has low density of electrons, it has a positive charge. So what happens? So we create a vacuum space. During those days, a vacuum space was created within the glass for free flow of electrons without any outside disturbance. So the electrons basically move from high density to low density, right? So the high density is basically cathode, low density of electrons is basically anode. So electrons move from cathode to anode. So in cathode, what we do is we create resistance in cathode to heat it by altering its properties. So by altering its properties, we create a resistance to heat the cathode so that the heat propels some electrons called thermionic emissions. We do this so that the flow of electrons from cathode to anode is constant. So that is the reason why we do this. And so that the electrons move in one direction only. So how do we create a switching effect through this? So basically, we apply voltage. So when we apply positive voltage, the electrons flow from cathode to anode. And according to the convention, the current flows from anode to cathode because current flows in the reverse direction of electrons. That is what the convention that we've adopted. So basically, from cathode to anode, the electrons are flowing and the current is flowing from anode to cathode. So in positive voltage, this happens. Similarly, when you apply negative voltage, then the electrons must now flow from anode to cathode, but this is not possible because in cathode there's a lot of generation of electrons and there's high density of electrons. So now because anode has low density of electrons, the electrons cannot flow from anode to cathode. So thereby what happens is there is no flow of current from cathode to anode because of that, and this leads to the device becoming an insulator. So when there is positive voltage, the device works as a conductor. When there is negative voltage, the device works as an insulator. So by just reversing the voltage, the device is acting as a conductor and as an insulator. So a switching effect is created. So cathode to anode, it acts as conductor. And anode to cathode, when because electrons can't move from anode to cathode, by reversing the voltage, you can make the device into an insulator. So by changing the direction of current, we're actually creating a switching effect. So this was how switching effect was created in the olden days, before semiconductors were actually discovered, and the work was before a research on semiconductor was actually commenced. This was actually before the semiconductors. But this is a very complicated process and it consumes a lot of space. So you can imagine a regular bulb itself is 2 to 4 inches. So you can imagine a transistor which is 2 to 4 inches. So if the transistor itself is 2 to 4 inches, then how large will the computer be? So the era of bulky electronics. So the first digital computer, because the switching devices, as I've told you, were pretty big. The digital computer was of the size of an entire room. Because a computer has lakhs and lakhs of transistors, right? So when it has lakhs and lakhs of transistors, and if each transistor is 2 to 4 inches, you can imagine the size of the computer. So because the switching devices were pretty big, the digital computers were actually the size of a large room. They were actually the size of a seminar hall. So which used during those times, the room-sized computer, it used 200 kilowatts of electric power. It consumed 200 kilowatts of electric power. You can imagine 200 kilowatts. And it has 18,000 vacuum tubes. 18,000 vacuum tubes. The cost is basically $500,000 or $5 lakh. The cost of this computer was $5 lakh, and no one could afford it. A lot of space, a lot of time, a lot of money. So the weight of this computer was actually 30 tons or 27,000 kilograms. So, and there were 5 million hand soldered joints in the computer. So that was during that time, during the start of the 20th century. But now, in the 21st century, we have laptops which are now in the size of a book, a small book. How is it possible? This is possible through microelectronic technology. So, this is possible, as I've told you, with the discovery of semiconductors. So, when semiconductors were discovered, the size of the transistors started reducing. Okay, the first semiconductor transistor was built by William Shockley, John Badin, and Walter Brattain in Bell Labs. Okay, so the first semiconducting transistor. This was built during 1947 in Bell Labs. So we change when we take a semiconductor device. When we take a semiconductor, we can change the semiconductor into a cathode and also into an anode. So we can change the semiconductor into a cathode that is of high electron concentration, or we can increase the number of electrons in one part of semiconductor, and in other part of semiconductor we can decrease the number of electrons. So the part where the number of electrons are of high concentration in the semiconductor will become the cathode, and the low concentration will become anode. Simple. So this is actually achieved. So the cathode is actually created, the cathode part of the semiconductor is actually created through N-doping. N-doping is actually done with the help of phosphorus. So if you take silicon, if you take the element silicon, if you take the element phosphorus, you'll understand that in silicon's outermost shell, there are actually 4 electrons. In phosphorus outermost shell, there are 5 electrons. So when you dope both of them together during N-doping, what happens is there are 1 extra electron is generated. So imagine doping lakhs of silicons and crores and lakhs of silicon and phosphorus. So you have lakhs and crores of free electrons. So when there are lakhs and crores of free electrons, you have a negative charge. You have high density of electrons and you have a cathode. So through N-doping, cathode is created. So the semiconductor device, silicon has 4 electrons, as I've told you, the phosphorus has 5 electrons, 1 electron extra. So when you dope both of them together, you have 1 free electron. So similarly, if you want to create an anode part of the semiconductor device, so anode means low electron concentration. So low electrons means high number of holes or positive charge. So this can be created, anode part of the semiconductor device can be created through p-doping. So p-doping is actually done through boron. So as I've told you, silicon has 4 electrons in its outermost shell, whereas boron has 3 electrons. So it needs 1 more electron. So what happens? There is deficit of electrons. So holes are created. So when holes are created, there's deficit of electrons and holes are created. You have positive charge. So in this process, a cathode and an anode is created in a semiconductor device. So the best example is PN diode. Okay. When you talk about transistor, you have PNP transistor. PNP transistor is nothing but it's a combination of PN diode and NP diode. So you have PNP transistor. So transistor is basically 2 diodes. So this is how you are actually creating a semiconductor device. You're making it work as a transistor, you're making it work as a diode. So the beginning of microelectronics revolution. So microelectronic revolution, basically, it began during 1950s. The cost of the transistors during 1950s was actually between $5 to $45, depending on the company and depending on the location. So the transistors cost during 1950s was actually between $5 and $45. It took $5 to $45 to produce the transistors, to buy it. And now the cost of transistors in 2006. So for 1 cent, imagine for 1 cent, you can get 1 lakh transistors now. So that is how cheap transistors are now because of the advancing technology. So during 1950s, the cost of transistors was between $5 to $45. And now, 2006, we are getting 1 lakh transistors in 1 cent. In 1 cent. You can imagine. So when you talk about the first phase was basically the age of discrete transistors. So discrete transistors means they were not manufactured on one substrate. So they were actually connected using a device like a breadboard. So they were manufactured, the microelectronic devices were manufactured separately and they were connected via a breadboard. So they were discrete because they were not manufactured on one substrate. So, for example, you have this 50 transistor radio. So it has 50 transistors as its name suggests. So 50 transistor radio is built by connecting transistors discretely using a breadboard. You can see the example on the PowerPoint slide. So some additional information. So voltage and current are basically directly proportional in linear devices, as we know that. So voltage and current are directly proportional. There is a linear relation between voltage and current. Okay. So what are the linear devices we have? We have inductor, we have capacitor, and we have resistor. So inductors and capacitors obstruct the direction of flow of the current, whereas the resistor, it obstructs the magnitude of flow of current. Okay. And you have non-linear devices where the relation between the voltage and current is exponential. There is exponential relation. So examples are diodes, triodes, and transistors and op-amps, etc. So these are some examples. So in the second phase of microelectronic revolution, you have integrated circuits. So they were invented in 1959 by Jack Kilby in Texas Instruments Company. Okay, so all the devices were actually built on the same substrate at the same time. So during this time, during this revolution, during this phase, all the devices were built on the same substrate at the same time. So same silicon substrate, they were embedded on the same silicon substrate at the same time. So there was same processing time, same processing environment, same processing temperature, same substrate, and the advantages are same working conditions. The working conditions for building everything is same. You can reduce the time. The same material is used. You can actually reduce the cost. Same substrate. So you can actually reduce the cost again. And working is predictable without distortions. The working of the microelectronic device or circuit that you've built is predictable now, and there's no distortion. And also the size, the most important point here is the size is reducing. So there is size reduction. Okay. So coming to the next slide. So basically microelectronics are advantages because there are advantages because of less size, because of the reduced size. So there are different stages of integrated circuits miniaturization. So the first phase, in the first phase, the technology was called 10 power minus 4 meter technology. So because the size of the smallest device during this phase was actually 10 power minus 4 meters. So in this time, 60 transistors, we were able to embed 60 transistors into one silicon wafer or one substrate. Okay, so 60 transistors we are able to embed into one silicon wafer or one substrate or chip. So, and the cost was actually $1 per transistor. So it is very costly. Similarly, in second phase, the size of the smallest device or transistor is actually 10 micron or 10 power minus 5 meter technology. So during this time, 2,300 transistors were able to be accommodated or embedded into one silicon wafer of the same size as previous. Okay, one substrate. And the cost of transistors at this point was 10 cents per transistor. So there is drastic reduction in the cost. In the third phase, you have 90 nanometer technology. So the size of the smallest device was actually 90 nanometers. So it can be a beamer. So here 170 crore transistors could be embedded into one substrate of the same size. And the cost is now drastically down to 1 lakh transistors for 1 cent. So that is the advantage of micro nano technology. So here we are talking about Moore's law. So Gordon E. Moore is the co-founder of Intel, and Moore's law is very famous, I guess. Every engineering student has an idea about Moore's law. So Moore says that in his law, he states that the transistor density on an integrated circuit or a chip, or the number of transistors on an integrated circuit or chip, the integrated circuit or chip has to be in the constant size. The size of the integrated circuit or chip shouldn't change. So with this being a constant, the transistor density or the number of transistors embedded on the same IC chip or same integrated circuit doubles every 12 months. Okay, the law says that the transistor density on an integrated circuit or the number of transistors on an integrated circuit chip, they double every 12 months or they double every year. So this was his prediction during 1965. But this law was actually valid only till 1975. But then during 1975, he had to change his law. He had to modify his law. So he now said that from 1975 onwards, he said that the transistor density on an IC chip or the number of transistors on an IC chip, they double actually every 2 years, not 1 year, every 2 years. So the number of transistors on an IC chip, they double every 2 years according to Moore's law from 1975 onwards. So you can see the curve. This was linear and then it slowly curved because, as I've told you, he had to modify it from 1975 because they were doubling only after 2 years. Every 2 years, they were doubling. So that's how we get 1G, 2G, 3G, 4G technologies. So when the size of the transistors are reducing, you get advanced technologies. So this law is actually still valid. It is valid till the 5G technology that we are using currently. So what is micro nanotechnology? So using tool set of advanced manufacturing processes, the technology through which we prepare or fabricate micro nano devices is micro nanotechnology. So here, friends, we have to understand that micro nanotechnology actually talks about the manufacture of micro nano devices and not the function of micro nano devices. So micro nano manufacture, the tool set of advanced manufacturing processes, the technology through which we prepare or fabricate micro nano devices is micro nanotechnology. So device functioning is not technology here. Preparing the device is technology. Preparing the device is technology. So when we say that the technology is advancing, so here we say that we have advanced technologies and all. So when we say that the technology is advancing, it means that we are getting the capability of making even smaller devices. According to Moore's law, we are able to accommodate even more transistors, even more microelectronic devices. So it's very important that we have to remember this point, that when we say that the technology is advancing, it means that we are getting the capability of making even smaller devices. So you can see that, the size of your electronic devices is decreasing. It has to decrease, right? It has to be friendly, user friendly. It has to decrease. It has to save your money, save your time, save space. So that is the benefit of micro nanotechnology.